Okay, today our seminar has a speaker from San Jose State University in California, Professor Plamen Koev. I should say a couple of words about him. He was a master's student in Sofia. Then he was a PhD student in Berkeley. Then he had a postdoc in MIT with under the supervision of Richard Stanley, and now he's a professor in San Jose, California. Okay, Plamen, please.
Well, thank you, Vesco, for
the
this
other people
opportunity.
Switch off the microphones.
Thank you so much for this opportunity. It's always great to say hello. We've had a great and very successful collaboration over the years, not just for my master thesis, but after the I no longer was at the Institute of Mathematics. So I ended up working in the field of numerical linear algebra. So we compute things with matrices, and it turns out that most of the problems in numerical linear algebra are actually purely algebraic and require some very heavy algebraic machinery. So it's been a very successful collaboration with Vesco and with other algebraists over the years who understand the algebra much better than I do. And we've produced some great results and published great work since. And so this is a work in progress that people have been stuck on, and we've made some progress here. So I'm here to share where we are, what still needs to be done, and what the challenges are in this field. Hopefully, again, somebody will say, oh, but this is trivial because of this and that. So the symmetric eigenvalue problem is one of the most important one in computing, because anytime you model something so often, the result is a symmetric matrix of some kind. Whether this is a covariant matrix in statistics or a stiffness matrix from mechanical engineering, somehow you end up with symmetric matrices all the time. And these symmetric matrices, through a very finite and very well understood process, are first reduced to tridiagonals. So, and this is where the infinite part comes in, because we know that from Galois theory that the eigenvalues, which are the roots of a polynomial for degree more than 4, you can't solve them. I can find these eigenvalues, but computers, of course, don't care about it. They don't know Galois theory, so they compute them anyway. Well, they don't actually compute eigenvalues. They compute approximations to these eigenvalues up to however many digits you have in your computer. So, but for all practical purposes, people that use eigenvalues, this is all they need. They don't need some complicated expression and an exact root. They need to know the sign and the leading digits, depending on the application. And so this is it's been a very active field of research. There's a number of algorithms that have been proposed. Even right now, they're going back and forth between what to put in LAPACK, which is the standard linear algebra library, which is public, and it's the engine behind things like MATLAB and whatnot. I'll explain what's going on and what the challenge is. And what we started looking is not so much in trying to get something more accurate and more eigenvectors that have the exact same mathematical properties as the computed eigenvectors that have the exact same mathematical properties as the true eigenvectors. And so this is where the number of sign changes in an eigenvector comes in. So most often, if you can preserve the mathematical properties of the object that you're computing, then it usually comes out correct. So this isn't provable. But anyway, this is the outline. So like I said, the first thing to do when you have a symmetric matrix is to reduce it to a tridiagonal matrix. I assume this being a algebra community, I'll just go over a few of the details of how this is done, and I apologize if this is something that is trivial to everyone. So whenever you have a matrix, so the first through a finite process, it's reduced to a tridiagonal. You start with the symmetric matrix, and then you apply a some type of an orthogonal matrix. It can be a given sortation, or it can be a house order transformation. Essentially, this is just a 2D rotation where you take a cosine, sine, minus sine, and cosine. So this is an orthogonal matrix. And these sines and cosines can be designed to rotate the first and the second rows of this matrix and create a zero right here. Now, of course, if we're computing eigenvalues, we'd like for this similarity, for this to be a similarity transformation. So we need to complete the similarity. And the way that you complete the similarity is by putting the exact same matrix, but transposed on the right. And now the eigenvalues of the original matrix and the final matrix are exactly the same. The zero that you create here by this rotation on the left, so when you create a zero here, you rotate the first two rows. When you complete the similarity on the right, this rotates the last two columns. I'm sorry, this is the last two rows, and then on the right, you do the last two columns. So the zero that you create here doesn't get affected by this process. Now, of course, if this matrix is symmetric, then it's this matrix times the symmetric matrix times the matrix transpose. So at the end of the day, this resulting matrix has to be symmetric. The zero here didn't get touched by the completion of the similarity, and because this has to be symmetric, so this has to be zero as well. And this is you can write the formulas for this reduction. So then you compute. Then you can continue with the with these transformations until you create zeros. So you do something like this. So you start with a zero here, and then you produce another zero here, and then finally a zero here, and then you're done. And you automatically get the ones upstairs. Now at this point, there's nothing that we can do to create zeros, for example, below the main diagonal through a finite process. The ones that we can write the formulas for, because if we could, this will violate Galois theory, that will actually be revealing an eigenvalue by virtue of an actual formula. And this obviously cannot be done. But algorithmically, this cannot be done. That even if you were to try to rotate, for example, the first and the second rows in order to create a zero here, which is our only option to create the zero, we rotate the first and the second rows. We create the zero here. But when you complete the similarity transformation, we have to rotate the first and the second columns, which will destroy the zero that we just created. So we're stuck with a symmetric tridiagonal here, and there's and of course we can have transformations. We can start converging to eigenvalues, which is exactly what all these algorithms do. And this is really the thing. We're trying to make all these off-diagonal entries here to get smaller and smaller and smaller until eventually they can be ignored, because even if you ignore them, the matrix with the ignored ones has eigenvalues that are very similar to the one that we started with. So this is how it is, and this is where the tridiagonal eigenvalue problem, as restrictive as it seems, like who really cares? It is a big deal. People have been working on it pretty much since the invention of the computer. It's still not a done deal, and it's unfortunate for several reasons. And here's what's happening. So what people want with these matrices are with computing eigenvalues and eigenvectors of tridiagonals. The eigenvalues are not a problem. The eigenvalues are done. You can get the eigenvalues extremely accurately to the precision of that the computer will allow you to, or nearly there. So this problem has been solved, and I'm not going to go over this. But suffice it to say that if you do the right thing, you can get all the eigenvalues extremely accurately and do so in optimal time. The open problem is still on eigenvectors. So with the eigenvectors, what people would like to do is, of course, is to get the most out of and pay nothing in terms of computational time. So the number one thing is to compute each eigenvector in order n time, where n is the size of the matrix. So you want one eigenvector, you're willing to spend about as much time as what you're trying to compute. And by doing so, we want to do this independently. We want to compute eigenvectors that are as accurate as the data deserves. So what does that mean? It means that the eigenvector should be such that it'll be not more different than if you're to take your data, perturb it a little bit, and if this changes the eigenvector by little, then this is the room, all the room that you have to work in. You want to compute an eigenvector there. But if you were to compute if you were to change the data in the matrix a little bit, but the eigenvector changes a lot, that's okay. You have all this room, how this changes to compute an eigenvector there. So the technical formula here that gives us the best error bound that is meaningful is to have the angle between the true and the computed eigenvectors be bounded between some multiple of the machine precision epsilon here and divided by the relative gap. So the relative gap for any particular eigenvalue is the smallest relative gap between the eigenvalue whose eigenvector you're computing and the rest of the spectrum. So in the ultimate case, when we have identical eigenvalues, then we have an invariant subspace in which you can find an eigenvector anywhere within that space. The idea of having an accurate eigenvector doesn't make any sense. This doesn't apply here because we'll have distinct eigenvalues because of the assumptions that we'll make. But at the same time, it gives us an idea if we have a cluster of eigenvalues that are very close, they don't have to be different by very much to be different, but it means that we're almost in the situation where we have an invariant space, but not quite there. So this is what this means is that we have so much room in which to compute this eigenvector that even if we were to compute an eigenvector with the perfect error bound, the problem is that when you compute another eigenvector, it doesn't have to be orthogonal to the first. And this is where the trouble is with this approach, is that people just like when they compute eigenvalues of symmetric matrices and symmetric tridiagonals in particular, they expect orthogonal eigenvectors, and the fact that the eigenvectors are orthogonal is innate to the problem. So if you have a symmetric matrix, it does have an orthogonal basis of eigenvectors. We know this from theory. Doesn't matter how close the eigenvalues are, these vectors should be orthogonal. Now, if the separation between the two eigenvalues is not small, so if they differ, but let's say if the relative gap is more than 10%, then the eigenvectors come out orthogonal. So if you have well-separated eigenvalues, then this problem has been solved. It's all about when you have clusters of eigenvalues, what do you do there? Because then the vectors, if you compute the vectors individually, even with the best possible algorithms that are available now, they don't come out orthogonal. And this is where we started looking at so what to do here. And the algorithms, so you can have two of these three properties, but not all three right now. So, or at least not all three guaranteed. So QR has been QR iteration has been the workhorse in this business for many, many years. And it works great. It produces orthogonal eigenvectors, it produces this error bound, but you have to be computing all the eigenvectors, and this will cost you order n cubed. Because you compute them all of them at the same time. You use orthogonal transformations. As you compute them, the vectors start out, remain orthogonal. There's no issue there, but people like faster algorithms. Can't blame them. Sometimes people would just maybe want few eigenvectors. So this is what people have called the holy grail in eigenvalue computation, to find an algorithm that satisfied all these three conditions. So they thought about 25 years ago, that they had solved the problem. This is right around the time that I was starting to work with Jim Demel on this problem on matrix computations, and they thought they had found it. It's this algorithm that uses something that is called DQDS. I'll explain what this is. It stands for differential quotient different algorithm with shifts. It seems to deliver all three things in most cases, but there's no proof. And in fact, every time they think that they figured it out, a new example comes in where this algorithm fails. So it's not done yet. There was a lot of excitement about it, that it could possibly be the one that'll satisfy. People do use it, but you always keep one in mind that in tightly clustered eigenvalues, you can have problems. They started thinking about introducing randomness into the system to just break apart clusters, but this still has issues. So yes, so for the computing of the eigenvectors, we can assume that the eigenvalues are already computed. But even if you assume that the eigenvalues are already computed, this doesn't help us very much, because if they're very close, just because you have an eigenvalue that is already computed, or several eigenvalues that are already computed, this doesn't help you very much with the computation of the eigenvalues, because it's the same thing as when you're computing Jordan blocks. You cannot compute the eigenvectors twice and expect a different result, because if you use one eigenvalue or eigenvector and another eigenvalue that differs only in one unit in the last place, you can run whatever algorithm you try, you're not going to get an accurate result. So what the property that there's one mathematical property of these eigenvectors that I've stumbled upon because I worked on totally non-negative matrices. These are matrices with all minors positive. I'll explain in just a second. So they have very interesting oscillating properties in the eigenvectors. Is that the ith eigenvector has I-1 changes of sign. So what that means is that the eigenvector corresponding to the largest eigenvalue is of the same sign. It can be all positive or all negative, and you can always multiply by -1 there, but it's essentially of the same sign. Then the first eigenvector is changes signs once. It starts out, let's say, positive and ends negative in the entries. And the last eigenvector will be completely oscillating. It'll go plus minus, plus minus, plus minus. So this is something that it turns out that you can guarantee, strangely enough. Of course, nobody cares about the number of sign changes because this usually involves entries that are very, very tiny, and they can switch from positive to negative if they're so super tiny. So nobody seems to care, but but we're getting very promising results in terms of orthogonality for when we run these things. And then I'll explain what this is. And then hopefully somebody will say, well, yeah, of course you get orthogonality because. Anyway, so the idea of computing by and preserving the mathematical properties of the computed objects is very long-standing. So and has been very successful over the years. And here's some examples. So the IEEE standard for floating point arithmetic was designed specifically with numbers that are called subnormal. So you have the floating point numbers that are designed the way that they are, but you have to add near to zero. You have to take the interval between the smallest floating point number that is designed the proper way and the zero, and split it up in smaller chunks just to make sure that if A is not equal to B, then A minus B has to not be zero. This is something that people expect. Not everybody studies what floating point arithmetic is, mathematics, numerical analysis, or let alone anything else. But computer scientists get on there, and again, can't blame them. And they need to divide by A minus B. And this is exactly what any normal human being will do. You will check whether A and B are the same. And if they're not the same, you'll divide by A minus B and thinking that this is okay, and you expect for this to be okay. It is okay now, but it wasn't okay in the very beginning when people routinely run into these problems. They're very difficult to debug. You look at your program and you have this check. If A is not equal to B, then you divide by A minus B, and it'll be very difficult to explain how it is that this is where you run into trouble. And so anyway, so this was fixed, and they designed it specifically, and it required extra hardware on the computer chips to implement this very part. So people found it worthwhile to do this. In another example, they figured out in the early days of computing that instead of just doing the addition, subtraction, multiplication, and division, they can also do something that is called a fuse, multiply, add. which means that you can compute like essentially ax plus b in one go. And indeed, if you look at how the multiplication is done on computers, adding something to a product isn't going to add any time. So you can indeed compute ax plus b in the exact same amount of time that it computes just a times b. But this got rejected, and it got rejected because then you no longer have commutativity. And people expect that a times b is equal to b times a. So for example, if you wanted to compute an expression xy minus xy, I mean, you totally will expect to get a 0, as you should. But if you compute the first xy first, and this is and get this to as a variable a, so fl stands for the floating point result of this, and then you compute the floating point result of the difference. So you compute the xy accurately, but it gets rounded because you compute the floating point result of this, and now you're subtracting the x times y minus something that isn't x times y, it's the computed value of this. But so this will be truly different from this. And so the floating point of this result won't be 0 most of the time. And so this got rejected right away. So you think how it is possible to that one fewer floating point error will actually be a bad thing? It is, because the arithmetic no longer does what you expect it to do. We've had great success with Jim Demel on computing with totally non-negative matrices, which is how I got the idea about the eigenvectors in the first place. This is to just start out with a matrix and create a 0 in it, but preserve the structure. So you start with the matrix and somehow get a similar matrix to it, which has the exact same structure, the exact same algebraic properties, but it's closer to computing the quantities that you would like. This resulted in the first algorithms for computing eigenvalues of non-symmetric matrices accurately, including negative eigenvalues. So and it's all the same idea: preserve the algebraic properties of the object that you're considering through the computational process. So so this is where we stand. The idea was to just get the eigenvectors with the correct mathematical properties, even if people don't care about them. They might actually be significant. Get the number of sign changes correctly, and then hope that we get orthogonality. We don't have a proof. We just have numerical experiments that tell us that things are way better than in any other situation. We don't have proofs yet. And both of these are determined very accurately, no matter how much you tweak your parameters, and then these notions are very robust. The number of sign changes doesn't change, and the eigenvector should still be orthogonal. So it's not automatic that you get exactly I-1 changes of sign in the ith eigenvector of a tridiagonal, but we can do this under several assumptions that we can make without any loss of any generality, and we will examine why it is that we get these I-1 changes of sign, and then replicate this in an algorithm. So the assumptions that are made is that the matrix, the tridiagonal, is positive definite, positive, and unreduced. So the positive definiteness you can get very easily by simply shifting the matrix to make it stays symmetric, but then all the eigenvalues that become positive. So you can very easily add whatever you need to in order to make it positive. This will also make the diagonal positive, because positive definiteness automatically means that the diagonal is positive, because the leading principal minors need to be positive. If you happen to have negative numbers where on the off diagonal, there is a simple similarity transformation that you can apply to make them all positive. So you apply something like this to both sides, and if you have a minus somewhere, it gets fixed. So this doesn't change computationally anything. So none of this is restricts our computation. So if you fix the signs and then compute the eigenvectors, then we can go back and apply the signs again at the end. Making the matrix positive definiteness positive definite doesn't change the eigenvectors at all. So this is something that has no direct effect on the eigenvectors at all. May as well be dealing with positive definite matrices. There's also the assumption for that the matrix is unreduced. So unreduced means that you don't have zeros anywhere in the off diagonal, because if you happen to have a zero, then this splits into two matrices. So this isn't really an interesting problem. You just split it, and then you're looking at a smaller problem, two smaller problems, but you're back at square one. So this is when you consider these problems, you assume that the matrix is positive, definite, positive, and unreduced. So the fact that the matrix is unreduced and all these betas are different from zero means that the eigenvalues are actually distinct. Whether they're distinct in when computed is another matter, but it won't matter because we won't be computing eigenvalues. This is to answer your question, Jose, is that so it will not, we actually won't be computing eigenvalues at all. We'll be computing differences between the eigenvalues, and those will always be positive no matter how tiny. So now that the matrix is positive, definite, and positive, this is something that is called a totally non-negative matrix, which means that all the minors of these matrices are non-negative. And you can very easily see this. This doesn't require any heavy proof. The only minors that are non-trivial are the principal minors, and we know that all the principal minors are positive because of the positive definiteness. And all the other minors will have some betas on the diagonal and whatnot. So the total non-negativity is automatic from these properties. Now, I've dealt with totally non-negative matrices for a long time, and they have a very, very rich theory, and very thick books have been written about them, and so they're very well understood. Unfortunately, not in a way that necessarily helps us compute anything with them, but quite a bit has actually happened. And this is what led us here. So who knows? Maybe this ends up being the thing that we care about. So here's what happens when you compute the eigenvectors of a totally non-negative matrix. So this is what they look like. So now you order the eigenvalues large to small. They're all different and positive, like we said. The first eigenvector corresponding to the largest eigenvalue is all the same sign. And we can always make this positive start out positive. So some people sometimes take the top entries and make them positive, and then go from there. We don't need to do this; it's irrelevant. So these are all the same sign. We have one change of sign in the second eigenvector. Starts out negative and then turns positive here. This starts out positive, negative, positive, and so we have a change of sign when we go from positive to negative. So this is no changes of sign in the first one. This is where the change of sign occurs here. This is the two changes of sign here. 1, 2, 3 changes of sign there. The last eigenvector has n-1. Every single spot changes signs. If we get a zero entry, then this can be counted with either sign, and the zero entries, as we'll see in just a second, always occur between entries of different signs. So it doesn't matter how we count the sign. If we're having a sign change, then it can be positive or negative or zero, and you can count it however you will. It still is one sign change. So this is a very well established theory and notion. People talk about this. You produce spy plots for these things where the reds are negatives and the blues are positives. And you look at these pictures, and again, you see all the same color here, alternating colors at the very end and everything in between. The reason why I do this is because when you start computing, so this is what, like 7x7 matrix. So you have some chance of computing things with the right number of sign changes. But when you go to the bigger ones, then so even a 30x30 matrix, so the first eigenvector, it is indeed of the same color or sign. The second one, you have one sign change, two sign changes, so on. Things are good. But the last one now, even for a 30x30, it should be alternating signs. It's not, and depending on which example you pick, but clearly examples as small as 30x30 cause these problems. So this should be all alternating. It is not. and clearly some signs or some entries there are simply of the wrong sign. And again, maybe in the round off it doesn't matter, but we will get them right. You go to 50 by 50, and again, it doesn't take much of an experiment to figure out that even there you run into epic problems. Even though the eigenvector corresponding to the largest eigenvalue has sign changes in it, and we know it shouldn't. It is the Perron root of a non-negative matrix. It should all be of the same sign, but this is what the algorithms compute nowadays. And the second eigenvector should have just one change of signs, and you see it has one here and another one here, just so many. So it says 1, 2, 3, 4 sign changes, even though it should only have one. The last should be alternating signs. It's anything but. So even with very modest examples, you see that the round off errors kill the number of sign changes. And so we looked at how can we replicate this? What are the mathematical properties that cause this to happen? And so this is where it's coming from. So it's all because of the interlacing of the roots of the polynomials because of the Cauchy interlace theorem. So if you take the characteristic polynomials of the leading principal minors and stick them into into a vector, so this is essentially just the number 1 because this is the 0 by 0 characteristic polynomial. Then this is just the characteristic polynomial of the leading principal. So this will be alpha 1 minus x, and so on. This is the characteristic polynomial of the anything but the last row and column. And if you take that vector, it turns out that there's a formula which tells us that if you're to plug in lambda I here for the parameter, then you get something that is proportional to these, where every entry is proportional to the to this vector, short for some positive constant. So essentially, the signs of these entries are coming entirely from the characteristic polynomials. There's some other factors that don't concern us here, but this is where the trouble is, and this is where this is what an eigenvector is. Again, short for some positive constants, but when we talk about the signs of the vectors, this is the only thing that matters. So the ith eigenvector, its signs come entirely from plugging in the ith eigenvalue into this vector. And it turns out it's all about the interlacing of the roots. We know that the roots of the k minus first characteristic polynomial interlace those of the kth, that is, if you were to erase one row and one column of a symmetric positive of a symmetric matrix at all, then the roots of the smaller matrix will interlace the eigenvalues of the bigger one. We know this, and this is where this interlacing comes in to establish the number of sign changes. And so we look at the number of sign changes in the sequence, and let's look at several elements, like 3 of them, k minus 1 and k plus 1 here. So 3 different elements here, and look at the behavior of the sequence around any one root of the middle polynomial. So if we're anywhere near the middle polynomial, this is where this characteristic polynomial will change signs, because all the roots are simple, because the eigenvalues are distinct. This is true also for the submatrices. So any time that this characteristic polynomial passes through a root, it'll change sign. So this is where things are getting interesting. So as this hovers around 0, then the observation is that when this is truly 0 or around it, then this polynomial and this polynomial are necessarily of different signs. And the reason for this is that the interlacing of the roots. So I drew this picture here. Is if you look at any one root here of the kth one, here's what the interlacing looks like. And because of the interlacing, k minus 1 will have one less root to the left of z than k plus 1. So this one has 3, this one will have 4. And this is exactly the situation all the time for any of the roots. Doesn't matter which one. For this one, it'll be exactly the same. But what this means is that if this polynomial here has one fewer root to the left of this z here than this one, this means that, well, it's the obvious thing, that the sign of this and the sign of this will be different. So if this is, let's say, a plus and a minus, it doesn't matter what this is. It doesn't matter whether this is a 0 or minus or a plus. The sequence will regardless of the situation, whichever one of these three situations we're in, this will have one change of sign. Whether it's so you have one change of sign is in plus plus minus, and also plus minus minus, and it doesn't matter if it's the other way around. And it doesn't matter if it's 0, because we're going to have to assign some sign to the 0, and you have plus and minus. Even if the 0 here, even if the plus and a minus is still one change of sign. And this is exactly where the it is the interlacing of the roots of the eigenvalues of the entire matrix and the submatrices that come into play here, and this is the argument. It's exactly what so the sign change only occurs when we have when x passes through a root, but then the number of sign changes here doesn't change in the sequence. So the only time that we get that a new sign change gets introduced in the entire vector is when we pass through a root of the last polynomial. So this is and this happens exactly I minus 1 times for lambda I. So lambda I, as it changes from minus infinity to lambda, it'll pass through exactly I minus 1 roots of this last polynomial, and this is how many sign changes will be introduced in this vector. So that's the interlacing property. That's where it's coming from, and that's the so in order for us to replicate this in practice, so we have to have these characteristic polynomials somehow have interlacing roots. So you compute something for like a 20 by 20 matrix just to see what's going on in practice, and then you realize that this is just a dream. In reality, you don't get interlacing. So this is a 20 by 20, the eigenvalues of a 20 by 20, and then you erase one row and one column. You should have like these should be between these roots from theory, and they're very close. So this is why I marked them as red. But you can see that that this, for example, has 913 at the end, and this has 910. So this is this one is actually larger than this. Even by little, but it doesn't matter. Like it still is larger. So these are not interlaced. Similar story here. You can see that this 42 is larger than this, and it works the other way around. So this with the 82 is larger than, it's smaller than the 85, and it should be larger. So this is what happens when you compute anything in practice. So this is kind of hopeless. That doesn't matter. All of these eigenvalues are very, very accurately computed for the two matrices. But that doesn't help us any with what we're doing, and so we were somehow going to have to compute the eigenvalues of the matrices simultaneously of the whole matrix and the submatrices in order to preserve that interlacing. So this is exactly what we're going to do. The standard trick here is, instead of working with the tridiagonal matrix, is to work with its Koleski factor. We know that it exists because it's a symmetric and positive definite. These are the right parameters. Parlet wrote a lot of stuff on this. I'm not going to dwell on this. So essentially, people compute the singular values and the singular vectors of the Koleski factor instead of the eigenvalues and the eigenvectors of the tridiagonal. Mathematically, it's equivalent. It doesn't matter what you do. It still works out just fine. And but these are just much better parameters to work with. So I won't go much into details as to why that is. But this has been a standard practice for a while. The algorithm that people use is they start out with the bidiagonal Koleski factor, and you pick a shift that is smaller than the smallest singular value, and you multiply them in reverse, subtract the shift, and then compute a new Koleski factor of the result. Here's the actual algorithm. I just put it on here just for completeness. It works on the squares of the entries, QI and EI. This is how it always is. You just open any book. That's what is there. I just put it here just for reference. And the goal here is as you pick shifts properly, and there's quite a bit of theory about this, If you were to pick this to be an eigenvalue of the entire matrix, that is a singular value of B, you're going to get a 0 here. You never truly get a 0 because you won't really hit it accurately, and it's never really a floating point number. But as you pick these shifts carefully, you can get this as close to as you can to the eigenvalue. So this would be about as close to 0 as you can get it. And you go from it usually takes 2 or 3 steps of this algorithm to produce a singular value of the matrix. You shift and then run the algorithms 2 or 3 iterations, produce something where it produces an entry that should be 0, isn't 0. You just go ahead and what the term is deflated, and you get a smaller matrix that now has 1 less eigenvalue. So you've computed the last one. And so this matrix here has eigenvalue. The eigenvalues are lambda 1 minus lambda n, lambda 2 minus lambda n, and so on, lambda n minus 1 minus lambda n. And so this is the next eigenvalue that you're going to get. So these are the different. So essentially, you don't get the eigenvalues themselves, but you get the differences between the eigenvalues, which is much more important. Because if the eigenvalues are very close, computing them isn't really helping any, but getting the differences is exactly what you need. And indeed, in these characteristic polynomials, the characteristic polynomials are products of differences of eigenvalues. It's exactly what you need. So this is computed very accurately to high relative accuracy. You get all the signs, almost all the digits correctly, and you can run actually all the way to the last digit, which is exactly what we proved, that this algorithm is monotonic with the sigma. So when you pick better and better when you pick better and better shifts, you get closer. You can get as close to a singular value or an eigenvalue you like until you're located between 2 consecutive floating point numbers. We call this a perfect shift, which is essentially the largest number that you can shift by without breaking positive definiteness. And we run it simultaneously on the matrix and its submatrices, and here's how it happens. So if the eigenvalues of B and B and its leading principal submatrix are the lambdas and mu's here, you first pick the perfect shift for the so here's B, here's its submatrix. This is the n minus 1 by n minus 1 submatrix. So this is the one that we want. Eigenvalues and singular values interlacing, and you run this dqds with the shift on this matrix and with the exact same shift on this matrix. So because of this monotonicity that we figured out, then it will definitely succeed here. And you only run it in theory. In practice, it turns out all the entries when you run it on the smaller matrix are exactly the same ones, except for the bottom right-hand corner entry, which turns out to be a little smaller than this. So this entry here should be 0, and this entry is smaller than this one. And so so on the next step, so we don't really need to run it separately on this matrix. All we need to do is compute one extra entry here for which is different from this one here. And now this one should be 0, isn't? We deflate it, and now you have this matrix and this matrix right here that you do the exact same thing on. It turns out that these algebraic relationships, that you still have some remnants bn minus 1 prime here, and the fact that this one is smaller than this one ensure that the smallest singular value now of this matrix, of the smaller matrix, is smaller than the smallest singular value on the one on the left. So if you were to, which means that if you were to run dqds on this matrix, it'll definitely succeed on this one. And we are only running them again simultaneously, only in our heads. In practice, they only differ by 1 element. So you run it on one of the matrices and you compute just the one different entry in the other. But what this produces is, so every time, because of everything is positive, we compute the differences between, not just between the consecutive entries of the consecutive eigenvalues of the whole matrix, but also between the consecutive eigenvalues of the submatrix. So we have a situation like this. So we have eigenvalues like this of the big matrix and eigenvalues like this of the smaller one, and we compute these differences here, 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 like this. And they're all positive, just because that's how it is. The smallest eigenvalue is always positive of these things, and so we compute these differences, and since they're positive, because the smallest eigenvalue of a symmetric positive definite matrix is positive, then all these sequences, all these differences that we compute are positive, which guarantees that the eigenvalues interlace perfectly and strictly. And then we can compute the actual eigenvectors through this formula with the characteristic polynomials. And the entries of these characteristic polynomials are, again, differences between the eigenvalues of the matrix and the eigenvalues of its submatrices. And from all these differences, we can assemble all of this and then get essentially perfect number of sign changes every time. So that part works great, but again, we're computing something that nobody cares about, so we started computing. Are we computing what we need to be computing orthogonally? Are these matrices actually orthogonal? So we designed some really bad matrices to essentially take the identity matrix and you put some epsilons just on top of it, just to this is about, I think, 10 to the minus 40. So to working precision, this matrix that we are computing the eigenvectors of has eigenvalues are all equal to 1 to full machine precision. Yet it computes eigenvectors with the correct number of sign changes. It's not exactly orthogonal. We would have liked this to be 10 to the minus 16th. We don't understand why this is. It's still sort of orthogonal, decent enough, but not exactly. I don't know why that is. So it's promising. We don't have a proof. We don't understand it. We're on experiments. It looks okay, as in like it's definitely not orthogonal, but they're not as orthogonal as you would like in that measure that everybody uses for what constitutes an orthogonal matrix. But that's where we are. So this is a joint work with one of my students. Came to visit from Gabon College. So thank you very much. And I hope somebody will say,
thank you very much.
Know what's happening.
Do you have some questions or comments? There is no need to raise your hand. You can simply speak.
No. So I see the questions in the chat. So no, none of this has been published. But we have a write-up of all of this with all the proofs of all these properties. That we just don't really feel that anybody really cares about eigenvectors with the correct number of sign changes until they're actually become orthogonal. So if anybody's interested, I'm happy to send the whatever we have preliminary here. But yeah, I don't think this is a publishable quality yet.
Some other questions or comments? Okay, I make a small comment. When in 1968, I became a first-year mathematical student, we started to study also some programming and to write some programs with 0 and 1s instead of these modern languages, etc., etc. But in that time, the idea was that if you have a good computer, you should not care too much about how fast are your algorithms, etc., etc. And in that time, we had to care our algorithms to be very fast because the computers were bad. But now I see that even with good computers, you need good algorithms to solve everything. I cannot imagine that you can solve some problems with 200 by 200 matrix. For me, this is incredible.
Well, they're doing millions by millions in the and even billions now with certain properties, and so the problem is that this turns out to be real money. So numerical linear algebra algorithms get used in everything from search engines to cell phones. Even figuring out which cell phone tower your cell phone is talking to is a linear algebra algorithm that decides it. So so when you're running a search engine and you're every time that you compute something, it is some energy, maybe a tiny bit, but it's so then it gets added up. So it becomes a faster algorithm. It's immediately money in the bank. It's the same thing with the cell phones. If your cell phone is running an algorithm that is more efficient, then first, even if it's not faster, it uses less energy, and your battery lasts longer, and then you're happier. So this is why this is a very active area of research. And anytime that you make any kind of progress at all, then it immediately gets applied, and everybody likes it right away because it means something positive for everybody.
I remember with Plamen and some other people, we tried to solve the problem to find that all polynomial identities for 5 by 5 matrices of degree 12 follow from the standard identity of degree 10. And for this purpose, we had to solve some really heavy problems from a computational point of view. And I remember that with him, we had to multiply 5 by 5 matrices instead to use the standard program for multiplication of matrices. We wrote this 25 program elements because it turns out that this is faster than to use some problems. But nevertheless, this problem took 8 hours in Berkeley in this Cray, which in that time was the fastest computer with 68 processors. So it was really, and I think that in that time they checked their methods to work with linear algebra. And I think that if we paid for this one, we should pay maybe $100,000 or something. But since this was a joint venture, we solved our problems and they checked their methods, so it was free. I think
these were the times, these different computers. And
yeah. Some other comments or questions?
I have a comment.
Yeah, sure, Rosanka.
So, as you said, eigenvectors and values are the algorithms are very important in searches, etc., etc. So I had to teach, not that I wanted, but I had to teach a course on information retrieval, primarily targeting computational linguistics students. So actually, eigenvectors are the major tool there, even for computational linguistics. So there, I don't remember what algorithm we used, but the important thing was, as you said, huge matrices. Each row represents a text, and the vectors, the columns, they represent the number of the current. This is an intuitive, simple explanation that I recall. And the columns represent for each document how many times this entry occurs in that document. And then the purpose is the first stage, and actually cyclic iteratively several times until you get as small as possible matrix. So you get not negative values, not the size, but as much as you can get zeros. The zeros, they represent that this item doesn't occur in that document at all. And then you reduce, you throw away those vectors which are irrelevant based on the number of the zeros in them. And then you repeat this until you get a good matrix, and then the documents are clustered depending on the values of the entries. But what algorithm I taught, I can't remember. So my major research is not data-oriented approaches to computational linguistics, but logical approaches. So
okay, you have one example that numerical linear algebra is useful also for your own topic, so it's okay.
Yeah. But last year's couple of years, I have been obsessed by an idea to put together logic approaches And what you describe here, eigenvalues and computations, that I know almost zero. I don't remember, not that I don't know, I used to know, but I don't remember the details from the algebraic point of view. So at first, one simple idea occurred to me. For propositions, for statements, instead the typical case is you have a relations and some objects in that relation, and it's either true or false. In logic, that is the proposition. But instead of that, I use a situation theory. So the proposition is when you claim that in a situation, because situations, context are very important. So actually I insert, instead of truth value in those classical propositions, I insert some probabilities, some values, probably what I had there. From documents, you extract items, whether those objects are in the relation or not, with what value that can be. But then I introduce a second level, so that will make a matrix, definitely, with eigenvectors, what I described. Each classical proposition, instead of true, false, one has to put some numerical value. And then the eigenvector matrices are based on propositions and objects, because it's not one proposition, but many propositions related. So the rows will be propositions, and the vectors, the rows will be...
Сангите и още един доклад, че изнесеш сега още малко.
Окей, да. Дай ми думата да се довърши мисълта.
Добре, довърши се мисълта.
Въпреки, че никой нищо не разбира, само аз се чудя как да го направя. В момента имам една приета статия, да го направя малко по-сложно.
Добре, айде.
На две нива го правя. Точно сега на 17-ти ми е дедлайна и да напиша там каквото ти ревюъра искат да го правя. Но точно е такова. Значи ти идваш точно на време.
Не записваш, нали?
Ти идваш точно на време с тая лекция. Изпрати ми референсис, как да започна да се спомня каквото... Предположи, че имам нула знание. Как да си спомня тия...
Да записваш, може